Nuclear physics question from the past paper, January 2017, Unit 5. So, in question 14, low activity seal radioactive sources are used in schools to demonstrate the properties of ionizing radiation. The three sources have been mixed up. The sources and the radiation that they emit out are shown in the table. Americium is there, that's emitting out alpha. Radium is there, emitting out alpha, beta, and gamma. And strontium is there, it's emitting out beta and gamma. What is meant by the term activity? So how we define the term activity? The term activity means how many radiations or how many nuclei disintegrate or break down per second, or basically you can also, when something is with respect to time, so you can use the term rate. So rate of emission, rate of decaying of unstable nuclei. That is refers to activity. A number of the nuclei, radioactive nuclei, disintegrate or decay per second. Describe an experiment, static with and even 6 marks. Describe an experiment using absorber of different material that could be uh, carried out to identify the sources. You must explain how the data collected could be used to distinguish between the three sources. So we have americium, which is emitting out alpha. We have radium emitting out alpha, beta, and gamma. And we have strontium that is emitting out beta and gamma. First thing, whenever you are doing the experiment related to radioactivity, you should always check the background count, background radiation. Because the background count, the background radiation, using a background radiation, we can make a origin and work out that if we place a paper, if the radiation reduced to background, it means that will be alpha. When we place an aluminum foil and radiation reduced to background, it means that will be beta. And if we place a lead, if radiation reduced to background or decrease, then it will be a gamma source. So first we'll record the background radiation, then we'll place a source in front of the radiation and detect that. The count rate, that is first thing. The background radiation, how we record the background radiation means detector without source in front. Then we'll record the radiation with a fixed distance, because the distance also affect the count rate. Distance between the source and the detector, that also affects the count rate. That's why it should be done with a constant or a fixed distance. Then what we will do, we will introduce a paper between the source and the GM tube. Or aluminum between the source and the detector. Now what happens if the paper or aluminum, it reduces? As we know, the first part, they mention the types of the sources and the radiation which they emit out. So strontium is emitting out beta and gamma, both are there. If it reduced to background, it means it is americium. The source is americium. If it reduce but not to background, so it can be radium or strontium. Then we'll place aluminum. So if we place a paper or aluminum, if reduce the count rate, then it will be, or to the background, it means it will be americium. So if the paper reduced to background, the count rate, it means that will be americium. And when we place an aluminum, the count will reduce, but not to background. Then it will be strontium. And radium is there because radium is emitting out alpha. If when we place a paper in front of it, if the count reduced to background, because paper will stop this alpha particle, means it will be americium. But if it was a radium source, alpha will be stopped by the paper. So what will happen? The count will reduce. So that will be radium, but not to background. Still there are other radiation. And when we place an aluminum, or when we place, basically the paper can simply use to distinguish between them, because when I place a paper, this will reduce to background, this alpha will be stopped, but beta and gamma are able to pass. And for this one, strontium, there is no change with the paper. Is it clear, this experiment, how to work out the type of the source from the radiation emitted out? The school has a gamma source with a stated activity. The activity is 185 kilobecquerel. The current activity of the source is to determine to be 25.7. Activity of the source always decreases because in the beginning you will have more radioactive nuclei, but with the passage of the time, the number of the nuclei decreases. So as the number of the nuclei decrease, the activity also decrease. So in the question, we have original activity, that is example A naught, activity at after certain time, that is A. Calculate the time elapsed since the source was produced, and the half-life is 5.26 years. The relation between the half-life and the time period, look, we have the formula A is equals to A naught e raised to power minus lambda t. the formula which relate the half-life and lambda, the decay constant. So lambda is equals to 0.69 because the half-life is equals to 0.693 divided by the lambda. So what we need a lambda first. The half-life is given 5.6 years. So lambda will be equal to 0.693 divided by the time interval, which is equals to 5.26. That will give us the value for decay constant. The activities are given, so you have to convert them, but like 185 is there. So if it is 185, it will be 185 exponent 3. Or because when you're taking a ratio, the unit conversion does not make difference to the final answer. So if I want to solve this, I will simply substitute the values. This is 25.7. The unit of the half-life, it's a time. So it can be minutes, it can be second, it can be hours. It's a time. The unit of the decay constant is reciprocal of the half time period, because you can see this is a constant number. Both are reciprocal of each other. So the unit of the lambda will be reciprocal of the time. But half-life can be in minutes, it can be in hours, it can be second, depending on what source you are using. Even years. So 25.7 and A naught, the original activity is 185. I'm not converting this, substituting kilo, because I have to take a ratio. That's why it does not make difference to the conversion, the unit conversion. That is, what is the answer here? 0.693 divided by 5.26. 0.693 divided by 5.26. 0.132. So 0.132, and the time we want to find how much time is there for this source, like from when it is produced, the time elapsed since the source is produced with the original activity of 185. So 185 is multiplied, other side divide, 25.7 divided by 185 is equals to e raised to power minus 0.132 t. Now to remove this e, we take a log, because the log and anti-log, they are like anti-functions of each other. So we'll take a log. The log with base e. You can also say ln. Look, when a simple log is there, log, it means it's having a base 10. And this log is having a base e, which is also ln, natural log. What is the answer for taking a log? When I take a log of 25, take the log with base e, so 25.7 divided by 185, and take ln of this. And ln will cancel with e, so this will be equal to 0.132 into t. What is the value for, first take a ratio 25.7 divided by 185, and then take a log ln. Minus 1.973, and that divided by 0.132, negative, because we need a time. This whole factor, as you mentioned, that is equals to minus 1.973 divided by, so it is 14.95 years. So the time elapsed since this source is produced, that is equals to 14.95. Normally we write in answer 3 significant, so you can round it off to 14.9 or 15. Is it clear? This one. So when the activity is given, you can use these formulas to work out the total time interval taken by the source to uh, change its activity to 25.7 kilobecquerel. Another question. In a nuclear power station, nuclear reactions release energy which is used to produce steam which drives the turbine that generate electricity. That is the mechanism of nuclear power stations. So uranium isotope which is 235 undergo a nuclear fission when it's struck by a slow neutron. Nuclei of barium and krypton were emitted along the three neutrons. This reaction released about 200 mega electron volt energy, most of which appear as the kinetic energy of the product. And because that kinetic energy, like these particles collide with a water molecule, increase the temperature of the water molecule, and that water turned into vapor or steam, which rotate the turbine, produces electricity. The first part is complete a nuclear equation. So we should have equal numbers. We want 92. So here we have 36. What should be the number? So that 92. So we should have 56 because 56 plus 36, that will be 92. And 3 neutrons are there. So 3 multiplied by 1, that's equal to 3 is there. 141 is there. So out of 235 minus 144, yeah, 236 because one more is there. So 236 minus 144 minus 3, that is equals to 92. That's right. Explain why energy is released in this reaction. Why there's a nuclear fission or nuclear fusion, both cases the energy released. So what is the reason for that? The reason is the mass defect. When we calculate the total mass of the reactant and the total mass of the product, we find a defect in the mass. Like example, when we measure the mass of the reactant and we measure the mass of the product, we find there's a difference in the masses. Like the reactant will have more mass. Example, this was having mass of 236, but when we find the mass of this one, it will be example 235. Not exactly like in 235.5 example. So what happened? The mass is decreased. So what happened to that mass which is decreased? That is converted into energy. That's why the energy is released in a nuclear fission reaction. So the mass of the product is always less than the starting mass or initial mass of the reactant. So due to the mass defect, the energy will be released. Explain why the fragment must move away from each other after the fission takes place. Why the fragment must move away from each other. Yeah, to conserve the momentum, they should move away from each other. If the initial momentum is having a certain direction, the initial momentum should be equal to the final momentum. So if initial momentum, as we know, like uranium is there, so if the initial momentum of uranium is 0, the final momentum should also be 0. So how the final momentum can be 0? So the fragment which are produced during this fission must move in opposite direction to conserve the momentum. If the one which is a lighter one will move faster, the one which is heavy will move slower. They will have the same momentum but in opposite direction, so that the final momentum is 0. The diagram represents a nuclear fusion reaction. So hydrogen and helium fuse together to produce, two isotopes of hydrogen fuse together to produce helium and neutron. Write equation in the space below for this fusion reaction. So what could be the equation? As the hydrogen are fused together, the two isotopes of the hydrogen, they result in a formation of helium, and there is neutron. Calculate energy release in joules when the fusion reaction occur. So how to calculate the energy release? Basically what we'll do, we'll find the mass defect. We'll find the mass of the reactant and we will find the mass of the product, and the mass of the reactant minus the mass of the product, that will give us the mass defect. And using the mass defect, we can work out how much energy will be released. The advantage that the mass is given in mega electron volt per c square, so we don't have to convert or find the energy, because that means that this is a energy which is produced if the neutron will convert a neutron with a specific mass convert into energy. So we'll calculate a difference in the masses. The reactant minus the product, that will give us the mass defect. But the final answer, we normally represent in joules. So hydrogen and helium will add these masses. Sorry, hydrogen isotopes will add the two masses, and then helium and neutron will add their masses, and then we'll take a difference. So difference basically like 1875.1 plus 2807.9 minus the mass of helium 3726.4 plus 939.6. When you take a difference, this will give you the mass in mega electron volt, 17 mega electron volt per c square. And after getting this mass, you have basically, this is the amount of energy which is released when this mass will convert. And so mega electron volt will just, mega means it will be 17 into 10 to the power 6 electron volt, and this electron volt will convert into joule by multiplying with 1.6 into 10 to the power minus 19. That will give us answer in joules. Explain why extremely high temperature are required for this reaction to take place. Again, the same answer, fusion reaction. Because why sufficient high? Because what we need, we have to overcome the electrostatic repulsion between the nuclei. So we need a sufficient or enough kinetic energy which can overcome this. That is why we need a high temperature. State two advantages of obtaining a nuclear power on Earth from fusion rather than fission. So compared to fission, what are the advantages of fusion? Number one, fusion, when we compare fission with fusion, the fission we have a limited supply or limited fuel as compared to that of fusion. And the second one, the waste which is produced during this fusion, that waste is not a radioactive, but the fission when we carry out, like we use uranium, polonium, these all are ra- radioactive, and once we undergo they undergo a fission reaction, the products are also radioactive. This one is January 2016. Question 6. January 2016, question 6. What could be the right answer? Yep. A radioactive sample is a beta emitter. Beta are able to pass through. A beta is not able to pass air only. This a thick card. So not only in air. So it is able to pass through thick card. Aluminium will stop beta. Lead will stop beta. Not air only. It can pass through more substances. That's why B is the right answer. The graph shows binding energy per nucleon. Look, the previous graph, as we discussed in the last session, it was for the mass per nucleon. See, the two graphs are actually mirror images of each other. The mass for per nucleon will be like this, and binding energy, because what happened if the mass decrease, that mass converted into energy, that's why the binding energy will increase. The graph shows how the binding energy per nucleon vary with the nucleon number for a range of isotopes. Explain why alpha particle or a helium nuclei is more likely than any other small nucleus to be emitted from a large unstable nuclei. So what could be the reason why alpha particle is emitted out when the radioactive nuclei are unstable? They tend to like radioactive element tend to emit out radiation. So when you compare, like these are the lighter particles, the lighter one, okay, hydrogen, helium is there, helium isotope is there, and they have binding energy. So the question is, when a radioactive nuclei which is unstable, it tend to emit out alpha, beta and gamma. So while likely it will give out helium 4, which is He. So why? Because it is having the highest binding energy per nucleon in the lighter side. When you compare this side, the elements which are given to you, so it is having the highest binding energy per nucleon on the lighter side. So it will be more stable. That's why it is emitted out from the nuclei. Look, what happened, as you have a radioactive element can emit alpha, beta and gamma. these are the radiations which it can emit out, alpha, beta, and gamma. So now the question is, why an alpha particle He4 is more likely rather than other small nucleus to be emitted from the large unstable nucleus. So what could be the reason, like why a large nucleus, why it is not emitting out lithium, why it is not emitting out, say, hydrogen isotope, why specifically alpha particle are likely to emit alpha particle? Because when you check these lighter atoms, other lighter atoms, they have low binding energy. So their nucleons binding energy per nucleon is low. So their not nucleons are not tightly bonded or binded in the nucleus. Compared to the helium or alpha particle, which is 4, it is having higher binding energy in this lower section. That is why more likely when the radioactive nuclei will disintegrate or decay, the more likely it will emit out helium 4. As you can see on the lighter side, this is having the highest binding energy, so more stable nuclei. Is it clear? Then in the next part, explain why fission reactor use isotopes of uranium 235 as a fuel, and you should include your reference to the graph. So with reference to this graph, why we use uranium, why not any other? Here we have uranium. Why we use uranium in the as a nuclear fuel, why not other element? Because as you can clearly see, when uranium will disintegrate, break down into lighter one, there will be a greater change in the mass. And then what happened to that, a greater change in the binding energy? So that greater change in the binding energy, that is released to the surrounding. So basically what happened, the massive nuclei, what they will do, they will undergo a nuclear fission reaction, and as they become a lighter one, the binding energy per nucleon, or the massive or heavy nucleus, have less binding energy per nucleon as compared to that of the lighter one. So as a result, what will happen, it will release energy to the surrounding. The number of this is having higher, lower binding energy per nucleon, they will have higher binding energy per nucleon, and the difference, what happened, the difference in energy will be there, and that difference in energy will be released. Because here what happened, the number of the nucleon, binding energy per nucleon, it means the energy divided by number of the nucleon. So the number of the nucleon is decreasing, that's why the binding energy per nucleon increase, and the defect and the difference in them, between them, shows how much energy will be released. In early part of 20th century, the Nobel Prize winner George D. Huxley use made the first use of radioactive tracers, and he studied the transportation of a small sample of isotope of lead in a broad bean plant. Complete a nuclear equation for a decay of a lead. So if you want to complete a nuclear equation for beta particle, this will be 0 and negative beta, so -1. Atomic number increases, but atomic mass will remain same. The half-life of the lead is 3.83 exponent 4. What is meant by the term half-life? The term half-life means it's a time taken by half of the radioactive atom or half of radioactive sample to disintegrate. Shows that the decay constant about 2 exponent -5, hence calculate the fraction of the original sample will remain after 86,400 seconds. So show that the decay constant is about this. So using a half-life, we can find a decay constant. So decay constant and half-life inversely 0.693 divided by half-life, I'll get the decay constant. And then we need a fraction like, so we have this formula n is equals to n naught e raised to power minus lambda t. So lambda we worked out, t is the time given. We need a fraction. Basically we need n over n naught. So n divided by n naught is equals to e raised to power minus lambda. What will be the, if you are not able to find the value of a lambda, you can use this value, which is 2 exponent -5 multiplied by the time we are finding for 86,400 second. What is the answer for this? The ratio n over n naught. E raised to power 2 exponent -5 multiplied by 86,500. So n over n naught is left is 0.178. And that's a ratio. So if it's a ratio, it will not have unit. The next part, energy release in this decay is 9.1 to exponent 14. Calculate the decrease in the mass. So mass defect is equals to mc square. Even in this one, you don't have to convert the units because energy is already given in joules. So 9.12 into 10 to the power -14 divided by speed of light square, which is 3 into 10 to the power 8 square, you will get the mass defect. The next part, the isotope of bismuth produced by a decay of a lead itself is a radioactive. It produces both alpha and beta with overall half-life which is small, much shorter than the of lead. Discuss how the decay of bismuth isotope could affect the measurement. Basically, lead decay into bismuth and bismuth in a short time decay into another element. So what will happen when lead will decay into bismuth? It is also emitting out radiation. So suddenly what happened? The activity or the count rate will increase. The last part, why material suggests why a material which is good absorber of neutron would enable the rate of fission to be controlled. Because what happened, we use a control rods. What is the reason for that? They reduce the number of the neutron which incident on the nuclei, the radioactive nuclei, reduce, so we can control the fission. So the material will absorb or reduce the number of neutron available to cause the further fission. That's how it controls that. The last part, fusion reactant could be better alternative to the